having made this little excursion into effect sizes, it makes sense to discuss meta-analysis a little bit. I'm not going to go into technical details on how you conduct a meta-analysis, but I will just say a few words about what is meta-analysis, why is it important, and most importantly, how can we understand the results of meta-analysis, because this is something that probably all of you will need at some point or other when you work on your master's dissertations. What are the problems that psychology is facing when we are trying to combine the findings of different studies and to make sense of what's out there in the field? Well, first of all, different studies use completely different statistics. One person used nominal scales and they applied chi-square tests. Another person used interval scales and they used correlations for the same kind of hypothesis or the same research question. Still another person may have compared samples, etc. Can we actually combine the findings of these studies? Can we compare them? And can we generalize over them? This is one side of the problem, but it's not even the hardest part, because the hardest part concerns the problem of diversity in the findings of different studies. In psychology, our sample sizes are often very small, and we fail to achieve high statistical power because also the effects are kind of small. And also, studies are very diverse with respect to settings, with respect to confounds and to extraneous variables that intervene with our reality that is being investigated. And the number of these variables that are potentially important is huge in psychology. This is why usually in many research areas there is a lot of diversity in the findings of the studies. So for example, you're starting to conduct a systematic review and you see that 6 studies have discovered an effect and 4 studies didn't. So the question is, does an effect exist? So the picture in research psychology is not unlike the picture that we've seen in Cinderella's little 5-trial experiment. So the bad and inefficient approach is to just try to read all those papers and to try to summarize those findings analytically. The good approach is to combine the findings of these studies statistically by using the procedures of meta-analysis, because this way you can make more precise conclusions. And research has shown that if you just do a systematic review without meta-analytic combination, you are very likely to make some mistaken conclusions at some point. The whole idea of meta-analysis is based on this very simple equation, that there is a dependence between 3 units of information that concern the findings of a study. Statistical significance depends on the size of your effect and the size of your study or the size of your sample. So the same correlation can be significant in a large sample and not significant in a small sample, etc. So as long as you have 2 out of 3 of those units of information, you can reconstruct the other, the third one. So for example, someone has published the correlation coefficient and you know the sample size, then you can always recover significance. Or if you have exact significance and you know the sample size, you can recover the correlation coefficient. So you can complete the missing information about studies. And it's important to summarize all the studies, even weak ones. So early 1970s, psychology was really facing this crisis because there were very many research studies. It was not clear how could they be all combined. They were all very different, and even the funders started to doubt whether psychology was a consistent replicable science because there was so much diversity in the findings. Luckily for us, several authors came up with different approaches to summarize, to combine findings of different studies. And these tools are called meta-analytic procedures. It's not a single approach, and there is no single author who created it. There are several authors who contribute different formulae to this toolbox. And since the end of 1970s, meta-analysis became hugely popular. So now you can find meta-analytic studies in all areas of psychology because they are very useful. What are the main tasks that meta-analysis are trying to achieve? There are basically three questions that meta-analytic studies are trying to answer. First of all, given all the available studies out there, what is the precise estimate of effect size based on all this combined research evidence? So we take, for example, 10 studies that investigated the correlation between, let's say, anxiety and academic achievement at school. Each study came up with a different correlation coefficient. Sometimes it was 0.5, sometimes it was 0.2, sometimes it was 0, or maybe minus 0.10. So we combine all these studies to arrive at a single estimate of this association with its confidence interval to judge whether this effect exists and how strong it is. Is it statistically significant? If this effect is statistically significant, and if we are interested in exploring it further, we can ask the second question. Are the differences in the findings of those studies completely due to chance? Or are there also additional reasons why the findings differ? If you remember our earlier discussion of G-power, you remember that there was a blue distribution which showed that in independent samples, the same general population correlation will take different values. So there is quite a lot of variation that we can expect in the findings of studies by chance alone. But sometimes there is more variation because maybe those studies come from different general populations. And at this stage, we take together all these correlation coefficients and we estimate the variance of these correlation coefficients. Are the differences between the studies significantly stronger than you would expect by chance alone? And if you see that the diversity of these findings is more than you would expect by chance, then we can ask the third question about moderators. What are the variables that could potentially explain the differences in the findings of those studies? Maybe some of them were carried out in regular schools and some in elite schools. Maybe they came from large cities or small towns. Maybe they came from different cultures, and so on. So all these differences between studies are potential moderating variables, are potential variables that could explain why in some studies effects are stronger and why in some studies effects are weaker. Technically, there are different approaches to conduct meta-analysis. There is the approach proposed by Rosenthal and Rubin, which is based on converting everything to z-scores, and it was mainly used in educational psychology, where Rosenthal comes from. Another approach was proposed by Hedges and Olkin. It calls to convert everything to Cohen's d. Our Hedges is G, which is very similar to Cohen's d. And then you correct these estimates and then you combine them. And this is mainly used in treatment research in areas that border with medicine. And the third approach, the most modern one, proposed by Hunter and Schmidt, it uses correlation coefficients, which are combined, and then these estimates are adjusted. This approach comes from organizational psychology, but nowadays it's most popular, I think, all over psychology. So most meta-analysis use the methodology of Hunter and Schmidt. However, regardless of what methodology you're using, the results are still going to be pretty much the same, even if the formula are somewhat different. So it doesn't really matter which approach you choose. So technically, when you do a meta-analysis, the calculation part is very simple and straightforward. You can even perform all these correlations by hand using Excel. They are not complicated at all. The hardest part is actually deciding how you are going to search for your studies, because you need to have very clear criteria, very clear keywords, scope in which database you're going to search, and criteria for inclusion. These are the studies that I'm going to include. For example, using specific measures or addressing specific research questions or specific variables. And the rest of the studies you're going to exclude. And then you basically download all those papers from databases. And it's not uncommon to go through 1,000 of different papers and only keep maybe 50 of them that corresponds to your search criteria. So it's actually a lot of work just going through all these publications. And then after you have collected the publications that you're going to use in your meta-analysis, you perform the abstracting part. You extract the information about effect sizes, sample sizes, significance from each study, but also maybe some key characteristics. For example, what kind of sample is this? What kind of measure of dependent variable is this? Is it self-reported or objective? Or whatever. Whatever can be interesting. And another stage, which is optional, sometimes we evaluate studies. If the studies that we find come from different journals, some really good ones and some really bad ones, maybe it makes sense to evaluate the study quality to make sure that good studies contribute more to our estimates of effects than bad studies do. But this is not often done, I would say. And then we combine those studies. When we convert effect size units, there are a lot of formula that we can use. Rosenthal and Hunter and Schmidt present them all in detail. Some meta-analysis use D, but nowadays almost everyone uses R for the main reason that if you're using correlation coefficient, the direction of association is always clear because there is always a sign. For D, the sign is dropped, and it's easy to confuse which group has a higher score, which group has a lower score. And also R is more flexible. Statistically, it's more convenient to work with. And there are many equations for different statistics that allow to extract this information and to convert the results of different studies. So for example, you can convert to Pearson R the results of a chi-square test, the results of any non-parametric statistic, which like Mann-Whitney test or Kruskal-Wallis, which produces a Z, or the results of student t-test, or the results of ANOVA, etc. And there are nice online calculators that you can use to convert between these effect size units. When you use some kind of online calculators, just be careful because they can use different formula, and sometimes the formula might not be quite applicable to your particular context or type of variables. So I would propose this nice calculator that you can see here on this slide, the link. Why is it good? Because it describes all the procedures that it uses, and it provides references to all the formula that it is based on. So you can always know what happens and why. And actually, the technical steps involve basically, in Rosenthal's approach, for example, it's very easy. You convert correlation coefficients to z-scores, then you average those z-scores, you calculate the boundaries of a confidence interval, using a very simple formula, and then you convert it back to Fisher. So this just is an example of calculation. So you can see that it's actually doable by hand. But of course, now you can use R. There are nice packages like Metaphor and RoboMeta. Those two are the most popular. Or I think there is also a module for meta-analysis in Jamovi, and in some other software packages you can find it. Not in SPSS, unfortunately. But I'm not going to discuss the technical sides of meta-analysis because very few people probably are going to ever do it. But I think almost all of you are going to look at meta-analysis, because if you find a paper in your field which is called meta-analysis, make sure you don't miss it, because it's a very important paper. It's going to use it's going to save you a lot of time and pain, because people have already collected all the findings and tried to generalize on them. So if you do it, you'll spend weeks and weeks and weeks going through all these studies. And people have already done it. Yoo-hoo. So just as an example of a meta-analytic study, this paper by Richardson, Abraham, and Bond, which presents psychological correlates of student academic performance at university. And they basically took all the research in educational psychology over 13 years, and they found 7,000 papers. But out of these 7,000 papers, they only extracted 241 datasets. So maybe one dataset could be published in several papers, or maybe many datasets did not correspond to their inclusion criteria. So in the end, they kept 241 independent studies. And from those studies, they retrieved about 1,000 correlations that they tried to generalize on. How do they present their results? Basically, for every meta-analysis, you will typically see such a table. And in this table, you will see there will be a dependent variable. Here, GPA, grade point average at university, not listed here because all of these are correlations with GPA. And here are individual variables that correlate with GPA. So for every association, for every effect, there is a number of studies that it is based on. Here, for example, locus of control, internal versus external. Internal locus of control, I believe the outcomes of my study depend on my effort. External, I believe they depend on luck or chance or whatever it is. So 13 studies, 2,000 individuals altogether, and the average estimate of a correlation is 0.13. Not so strong, but the confidence interval goes from 0.4 to 0.22, suggesting that this association is statistically significant. And these are the main results that you need. Then there are some additional results, like I-squared and Q are tests of variability. Basically here finding that this variability is higher than you would expect by chance. Rho is usually estimate of correlation adjusted for unreliability of measures, because in some studies the questionnaire of locus of control could be bad with Cronbach's alpha of 0.60, and another study is a good one with Cronbach's alpha of 0.80. Obviously, you need to adjust these correlations for reliability before you combine, and this is what is done here. And some trim and fill procedure to correct for publication bias, but it's kind of optional. So you just go through these effects and you can explore this table, or you can explore it in graphic format. Most meta-analysis also present what is called a forest plot. It's the same information that was given in the paper. For every variable associated with GPA on this horizontal axis, there is a point estimate of effect size. For example, for depression, it's about minus 0.10, very weak correlation between depression and GPA at university. And the line shows confidence interval. For depression, it includes 0. So if you are depressed, don't be disappointed. It has no effect on your academic achievement, probably. Yeah, and you can see that for some variables, even though the effect is fairly strong, the confidence interval is huge. Like, for example, peer learning. Basically learning from your friends, your classmates. You can see that confidence interval is huge, suggesting that probably it depends on who your peers are, whether they are helpful or not, etc. And for some effects, you can see like great goal, huge effect. Yeah, so it's very easy to kind of make sense of this area based on this forest plot. So I hope that you have some idea of how to understand, how to read meta-analysis. Sometimes in addition to this main meta-analysis, they will also include moderator analysis, where they will explore the differences in effect sizes depending on different variables. And these moderator analyses are presented either in the same kind of table where these studies are just split into groups, or in the form of a forest plot. So it's still quite the same kind of information. Of course, when we use meta-analysis, it's important to remember their limitations. First of all, there is publication bias. Strong and significant findings are published more readily than weak and non-significant ones. So sometimes when people compare, for example, the studies published in journals with the studies presented in PhD thesis, they see that the average effect size is hugely different, because in a PhD thesis you are supposed to report everything that you get, whereas in a journal paper you only report something that reviewers like, probably something strong and something more significant. Luckily, there are some ways to address publication bias. You can visualize publication bias using funnel plot. It's basically a plot. Horizontal axis is effect size, vertical axis is sample size, and each point is an independent study. So this line denotes average effect size based on all these studies. And for studies using large samples, the estimates are fairly close to this combined effect size. For small studies with smaller samples, these estimates are supposed to be more diverse, but you can see that small studies with low effects are less likely to be published because these effects failed to reach significance. And if you see this picture, you can conclude that there is some publication bias and use some trim and fill procedure to fill up the missing portion of this distribution. Unfortunately, it's a very confusing area because some people argue that publication bias in most cases does not really bias the outcomes as much as we would be worried. And other people argue that it biases the findings, but none of the approaches to compensate for publication bias are perfect. They don't really do a good job. So this is still an area in development. Among other problems of meta-analysis, we need to remember that it adds up apples and oranges. It adds up all the studies using different kinds of indicators, different kinds of interventions. So in the end, the outcome of meta-analysis is some kind of average temperature in the hospital. Sometimes you always need to be careful and to think what kind of studies are there. Luckily, nowadays, people mainly use moderator analysis to kind of try and make more sense of their findings. Sometimes bad studies are combined with good studies. If the quality of the studies is not evaluated, this could be problematic. And an important limitation is that meta-analytic studies usually focus on individual variables, on associations between pairs of variables rather than on the big picture. Luckily, nowadays there are also more advanced methods when people can take correlation matrices from different samples and kind of combine them, creating a larger correlation matrix where you can use a meta-analytic regression or meta-analytic structural equation modeling even. But this is technically difficult. This is computationally not so easy, and this is rarely done so far. And of course, the main issue is that some studies fail to report effect sizes. I tried when I was younger in my graduate school to do a meta-analysis based on a bunch of Russian studies, but unfortunately it was impossible because most people did not really even publish effect sizes. They would publish, you would know sample size and approximate significance. And you cannot perform meta-analysis with this. Luckily, nowadays the situation has changed because since about 2010, in the 6th edition of the publication manual, the APA makes it mandatory to publish effect sizes. It's very strongly recommended. Now almost all good journals demand it. And if you review a paper also, it makes sense to ask the authors to present effect sizes if they didn't do it, because this will facilitate meta-analysis. This will allow for better generalization in science. So we have reached almost the end of today's lecture. As always, there is some literature that you can explore. If you're interested in the critique of null hypothesis testing approach, there is a nice chapter by Kirk in the handbook by Davis. So look for the file called Davis 2003 PDF. If you're interested in the new statistics, effect sizes, confidence intervals, meta-analysis, there is a great book by Geoff Cumming, who was one of the members of this APA task force for new statistics. And he wrote this very accessible book aimed for undergraduates in very easy, simple language, very visual. So if you'd like to understand it better and you feel like you need more support, it's a good source. And if you want just a quick introduction to meta-analysis, there is Rosenthal and Di Matteo or Field and Gillett. But of course, if you want to actually do meta-analysis, look for good reviews of packages in R. There was a very nice 2017 paper which reviewed RoboMeta and Metaphor and some other packages. So I totally recommend to explore it because there are many good tools. And the tools that are state-of-the-art, they change every year because it's such a rapidly developing field. And for those who are extremely interested and motivated, there is an additional bonus track on Bayesian statistics, which you can feel free to explore if you like, but it's completely optional.